I'm Ben Hatton, and I'm an associate professor in material science and engineering at University of Toronto. I run the functional adaptive surfaces group. I would say there's two big areas that we're interested in. One is bio-inspired materials and bio-inspired engineering, and also material surfaces. I'm really interested in material surfaces and interfaces. My undergraduate was at Queen's University in metallurgy and material science. From there, I went to McMaster and did a master's in layered ceramic composites in the fracture, trying to get cracks to go sideways instead of all the way through. And then I did my PhD here at University of Toronto on organic, inorganic nanocomposites and how do organic templates direct the growth of inorganic materials. After that, I spent a couple years at Bell Labs, and then I spent 5 years working at Harvard School of Engineering and Applied Sciences and the Wyss Institute for Bio-Inspired Engineering. We developed a material called slips, which is a very slippery surface that really nothing can stick to. So I started here at U of T about 10 years ago, 2012. As a professor. We're very interested in things like medical devices. So medical devices such as this is our rubber catheter tubing, or this is an endotracheal tube. Medical devices like this very often develop bacterial colonies on the surface known as biofilms. And so how is this material science? Well, we can design the materials that the bacteria are interacting with. So one of our interests is in the design of antimicrobial surfaces for medical devices, but also things like the transmission of bacteria by hand contact from one surface to another within hospital environments. We have a project right now looking at defects within the surface of medical devices and how does the deformation of the device change the defects on the surface that the bacteria attach to. We have a number of projects involved with what we call large area fluidics. So confining fluids within material systems to change material properties. So we're very interested in designing more energy efficient buildings that can change the conditions of their outer facade or their skin as environmental conditions change and as solar conditions change. And so things like solar heat gain become a real problem, and the energy to cool the building, for example, in air conditioning becomes extremely high. So we're thinking of really more of a bio-inspired design where a building can actively change its surface properties in response to changing environmental conditions. So we've designed some large area fluidic layers that have a very thin confined layer of fluid within a material, meaning that the optical properties of that layer can change according to the environmental conditions, and our simulations show that this can do a great deal to improve the energy efficiency of a building and the operational energy requirements. Two of the courses I teach are MSE 440, which is biomaterials. And in that course, we look at the design of things like medical devices, this is a hip implant, and the choice of materials and the design of these devices in the body. So we look at a wide range of different medical devices and why were those materials chosen, what's the rationale behind it, and sort of what is the mechanism, the interface between the material and the body. I also teach MSE 401, which is essentially material selection and design. In that course, we look a great deal at the materials involved in product design and device design. What are the performance requirements for different products, and how do we suit the material selection to improve the efficiency of that product, but also sustainability.